Yeah, hi. Good evening, everyone. So welcome back to the live session. We have this is the second live session for this course. So now almost half of the course is completed. So I think the current week is a week 8 is running, and you have already completed the 6th week of this course. So this session is regarding the feedback. Okay, if you have any feedback for the course, and if you have any query, any type of query, if you have, you can clarify in this, and then we will discuss about the content, basically the concept which we are covering in the latest week, like week 6, 7, 8. Okay, then we will discuss some idea of that. Before starting the session, if you have any query, you can just ask. You can also post in the chat. We haven't received any query in the form, so generally we shared some form link with the session invite, but we haven't received any query, and we have also not received any query for on the forum. So if you have any query right now, so you can post in the chat as well, or you can open your mic and you can ask directly. Any query, anyone? Okay, so let's discuss the course things. Let me share my screen. If no query, so I hope my screen is visible. Can anyone confirm in the chat or by mic? Okay, thanks. Okay, so now the week, you can see eight is going on. Now the remaining 4 weeks are 4 weeks. So we have only content in week 9 and 10. So as you have already seen, the week 8 is the max flow network flow. Okay, and we are covering some questions on based on this max flow. And week 9 will also be remain on the same topics, but that will be the different topics little bit. So like minimum cut related to this. Okay, and after that, week 10 will be the DP, dynamic programming, which is also very important topic in the competitive programming. So that will be week 10. After that, there is no new content in the week 11 and week 12, and but assignment will be there. Okay, so assignment will be there, as dynamic programming is a very much important topic for the competitive programming. So we will give the assignments in week 11 and 12 also, based on the DP concept, which you will see in the week 10 content. Okay, so this is the course structure, remaining course structure you have, and only week 9 and then week 10 content. After that, week 11 and 12 will be the only the assignments based on the dynamic programming. So this is the remaining structure, and currently what week you are learning. So you can see week 6 was the BFS and BFS algorithm. Week 5 was the basically graph algorithms are started from the week 5, and more than this, so week 4 was the DSU. So, but week 5, where the we you have seen the BFS and DFS. So, what I hope you know the concept of BFS, DFS. So, these are some traversal algorithm basically. So, concept of these algorithms are generally traversing the algorithms. Now, what type of problems can be like created based on these traversing concept? So generally, you can think about that, like we are connecting some nodes to via some network, or now you can think about like a map, Google Map, or somewhere where you can consider like city as a node and the road as a like edge in between them. Okay, so you can relate the any type of network in the form of graph. After that, how you can traverse each node. Okay, what are the algorithms you have for to traverse each node in that graph? Okay, so in the programming problem, competitive programming problem, you will get some scenario. That scenario will contain some graph structure. Okay, in the any form, it may be a computer network, it may be a city network, or it may be any type of network, but that will form a graph structure actually. Okay, after that, if you want to traverse each node, so what are the algorithms you have? So these are the algorithms, basically BFS, breadth first search, and DFS, depth first search. Okay. So breadth first search concept, I hope you know. Let me just quickly recap. So we have these notes. I have also shared the link in the previous session as well. So I'll share again. You can recap the concept of basic concept of graph. So like BFS concept is, one second. Picture is big. Okay. And then- Okay, so BFS algorithm you can see here. So conceptually BFS actually start, you can start with any node. If source node is not given, suppose if source node is given, you can start with that node. After that you traverse the node that at adjacent label wise only. Okay, so like in this you can see the scenario of this graph. Okay, suppose you have this graph, so how that algorithm is actually work. So suppose you are starting from the zero node. So first we will traverse all the nodes which are adjacent of this zero. Okay. So we generally use the queue data structure for this. And after that, we just maintain that we will complete the adjacent label first, then we will move to the next adjacent label. So to maintain this things, we use the queue. Okay. So you can see first zero we are traversing, then after that we will traverse one or two. Okay. So if we are traversing one, then we will traverse the two. Okay, so this one is traverse, but we are looking that what are the adjacent from one and one of that is three and four. So after zero, we are traversing one and two. Then we will look for the adjacent of one, so that is three and four, and then we will check for the adjacent of two, but both three and four are already traversed. So we will not visit any node which have already visited. So order you can maintain like 0, 1, 2, and 3, 4. This will be the order in this. So this algorithm we will apply in this complete or all nodes, and we will get the sequence, and we will mark that our nodes are visited. Similarly, we have the DFS algorithm. So DFS follow the different approach to traverse the graph. So that actually traverse the depth first. Okay, that traverse the depth first. So if you see the structure of the algorithm, so we have this zero node we are starting from. First, we will look any one of the adjacent, and we will complete the depth where we can reach. Okay, a maximum. Then we will only return back, and we will follow the different possible depth. So suppose here we have the two adjacent from 0 to 1, 1 and 2, and then we will pick one of the adjacent, like one we are picking, and then we will check the next adjacent from this one. We are not going to 2 here. We will complete this depth first. So suppose we are moving to next node is like 3. Okay, then we will look where from we can move, where we can move from 3. Okay, so now 3 we can move 2 or 4. So suppose we are picking the 2, then we will check where we can move from 2, then we will move. Okay, so here we are getting like 0, 1, 3, 2, 4, this type of order. Okay, so these are two different types of techniques to traverse the nodes. Okay, task is same, but approach is different. So these two algorithms, you can see how you can implement. So in generally DFS, we use the stack externally, or we use the recursive algorithm that maintain internally stack operations. Okay, so you can go through this basic algorithms and then apply the same algorithms in your competitive problems where you're getting this type of requirement. Okay, so these are the basic, and another is like in the course. So BFS, TFS, okay, and then in shortest path. So another related problem which is very common also. So that is I'm also discussing here. That is topological sort. Okay, so like this is also very related to the like this BFS, TFS algorithms. Okay, what are the applications for these like BFS, TFS? So generally we check connectedness. Okay, so how many nodes we can reach in our graph. Okay, so like we are checking that how many nodes are connected to the graph. Okay, if we are starting from any like source node, where which node we can reach. So this is checking basically the connectedness. Okay, and these things we can check. We can also figure out the cycles. Okay, using these algorithms cycle we can check, and we can also figure out the shortest path in the terms of number of edges in the path. So so which algorithm is suited well suited for this? If we are looking the shortest path in the terms of minimum number of edge in the path. Okay, suppose we are looking the what is the shortest path from zero to all nodes. So here weights are not given. So so this type of problem generally consider that how many hopes are in between, how many edge are in between. So this type of questions. Like suppose we are asking that what is the best possible path in our like network or road network where the minimum number of hopes are coming in between path. Okay, or maybe you can just like see the railway network, so where the minimum number of stations are coming in the path. So this type of query you can solve with the help of BFS. So here, if you will apply the BFS algorithms, you will get the a label wise. Okay, you are just visiting label wise. So you will get the shortest path in the terms of number of nodes or number of edge in the path. So this algorithm is best suited for this. Okay, so this type of problems you can see where and also you can see the path. You can figure out the path also, and by maintaining the parent information. Okay, so which suppose if you are traversing 0 to 1 and 1 to 4, so you can during this process you can also maintain the parent of each node. In that way, you can figure out the what path you have actually following to come to on that. So generally, these traversal algorithms generate the tree. So where one path is possible from root to every node. So by storing the parent information, you can also figure out the exact path. So this type of scenario, you can use this algorithm and this topological sort. So before topological sort, I'll just discuss that what is DAG. Okay, so DAG is a graph where actually there is no cycle. Okay, there is no cycle. So this is called as a directed acyclic graph. This is a directed graph, but there is no cycle. So in this type of problem, we can use topological sort. And suppose what type of problems we can solve with the help of topological sort. Suppose you some dependency based problem. So dependency means suppose if you are planning for course, okay, where some course have the like prerequisite. Okay, so that means if you are picking like a B course, you have to first complete the A course. Okay, without completing the A course, you cannot pick directly the B course. So this type of suppose dependency is given. So how many what order you can follow to pick the course, and suppose you can also figure out that what are the minimum number of semester or terms required to complete the course. So this type of problems where some dependency is given. Okay, some dependency is given, and that forms a. If you just make a graph for this dependency, so that will actually form a directed acyclic graph. So like this type of graph. Okay, so suppose this is A, and after that you can after completing of this you can complete the B and C. Then after completing B and C, you can complete D, and then after completing C you can complete E, like this. Okay, this is a directed graph, and like this. So F. So this is a directed acyclic graph there. Okay. So in this, how you can figure out that suppose if you can what order you can follow to complete this. Okay, so you can only pick like this A first. Okay, because you cannot complete any other course directly. Okay, so without fulfilling the prerequisite. So A doesn't have any prerequisite, so we can pick this A first. After that, when we complete this, so this dependency will be removed. Okay, then we have the two choice. Either we can pick B or we can pick C. So in this way, you can pick any one, and later you can pick the other. So here multiple order are possible. So any order which you can calculate, that will called as a topological order. Okay, suppose if you are picking A to B, and after picking B, this will also be removed. So you can pick either C or D. Or suppose if I am picking C, okay, then this will also be removed. And after that, I can pick D or E, anyone. So I'm suppose if I'm picking D, then this will remove, but still F is not free. Okay, so then we can pick E. And when we will pick E, so this will also remove, and then we can pick F. So this is the one possible topological order. So this type of question is also asked generally in the competitive programming. So what if dependency data is given, then what order you can follow to complete all these? So any one of the possible order you can repeat. And another is possibility is you can also figure out that suppose in one term you can pick any number of course to complete if that course doesn't have any dependency. So here we can start with the 0 degree. So first term we can pick A because that is doesn't have the any dependency. After that we can in the next term or semester when we will complete A, so B and C now become like there's no dependency. Okay, so that dependency is completed. So B and C we can pick in the another term. So this is the first and this is the second semester. Okay, after completing this, we can select D and E. So E like this. Okay, and finally we can complete F. So total 1, 2, 3, 4. 4 semester we can complete these course. Okay, so if condition is given that we can pick any number of course in one term. So this type of also a one scenario where you can use this topological sort. So generally what concept we used for this? So we actually maintain the in degree. Okay, in degree means how many edges are coming to that node. That is called as a in degree. Okay. So to for this order, we maintain this information, in degree information for each node, and then we pick the node which have the in degree 0. Okay. And suppose you can see we are picking the node with in degree because there is no edge coming on this. So we will pick this. After that, we will update all the in degree of the adjacent of this. Okay. So that we will reduce by 1. So after picking this A, we will update the in degree of the adjacent nodes. So suppose this in degree has 1, this is also 1. And when we will complete this, so we will reduce by 1. So 0 and now 0. Okay. And we will take the repeat process again. So we will pick the again that node which have the in degree 0. Okay. So B and D will come in this. Then we will update the their adjacent and reduce the in degree by 1. So this process we repeatedly follow to identify that which node we can pick next. Okay, so dependency based problems can be like created based on these concepts in the graph. So this is the one important topics of the graph. So this link I'll share in the chat, so you can take the help of this to revise the concept if you have not seen. So now next is so this is the traversal algorithms and this topological sorter. And next week, I think week 6, you have seen this shortest path. Okay, so shortest path, one of the version I have already mentioned you. So that you can see this, which is discussed this single source shortest path. Okay, triple SP, single overview BFS revisited. So BFS revisited is actually BFS we can use if all the S have same weights or no weights. Okay, and we are looking for the shortest path in the terms of number of hopes or nodes in between or number of edges in between in the path. So this is the BFS, but what if the weights are given? Okay, then we have the different problem. So suppose if each edge has the like weights, and now we are looking the shortest path. So this is more actually real life of problems. So here we are looking the shortest path from one city to another city. Okay, there are multiple possible paths, but we are looking the shortest distance path from one city to another city. So here we are not counting the number of vertex or number of edge in the path. Here we are looking the total sum of weights in the path. That should be minimum. Okay, so but here there is a like some problem with that may contain the negative cost on the path, and some may also have the negative path cycle. So there are multiple scenarios are there, but we have different problems for that, different algorithms for that. So first type of problem is single source shortest path. So single source is given, and we are looking the shortest path for all remaining destinations. Okay, so like suppose you are framing the real life problem into a graph. Okay, so that graph may be directed or undirected, but you are taking only once as a source node and another are as a destination. So that is called as a single source shortest path. and we can use two algorithms. So first is like this Dijkstra's algorithms, and this is the weighted graph. Okay, so we can use the Dijkstra's algorithm. Another is Bellman-Ford algorithm. So both task is same, but approach is different. Okay, but Dijkstra algorithms has some constraint like that. So that this algorithms may fail if graph contains the negative weights on the edge. Okay, so this algorithms may fail. It may correct also, but it may fail also. So we generally not use this algorithms on the negative weights graph. Okay, negative weight cycle. Negative weight cycle means suppose if you have A, okay, B like this, and C, okay. Hmm. If you this is a cycle, but if you add this like add all the edge of this cycle weight, so like this is 10, this is -5, this is minus 10. If you add all these, you will get a negative weight total sum. Okay, so that is called as a negative weight cycle. Okay, so 10 minus you will get total sum is -5 of this cycle. Okay, so this is a negative bit cycle. So actually, no algorithms works for this because if we will use this algorithm, so always you will get a shortest path if we will repeat this. Okay, so if we are moving from A to B, then B to C, then B to C to A, so A will again update, and if you will repeat this cycle, then it will more reduce. So that generally is not a good scenario. But digital algorithms also fail if a graph doesn't have the cycle, but that has the negative weights only. Why that happens? Because this digital algorithm is actually greedy algorithms. So in the approach of this digital algorithms, if we are looking for any vertex, so approach is simple. So let me just give the idea of approach. Hmm. Suppose if you have this vertex. Okay. Like you have this 4 and this 1 and this is 7. Okay, so how this algorithm is generally works, so we start from any one single source, and then we looks what are the adjacents. Initially we initialize with 0 and infinite, okay, all the distance. After that, we pick the vertex which has the minimum distance. So A is the minimum distance. Now we check the adjacents. So what are the adjacent where we can move? So A to B, we can move A to C. Okay, so let me make this C. So we can move from A to C also. Okay. So now if we are moving from A to B, so we are getting the distance, current distance is 0 at this node, and 0 plus B 4 is 4. So means in 4 distance we can move from A to B. Okay, so this will be updated because we are getting the less. And here A to C, we are getting 0 plus 7. So this will also reduce because we are getting less 7. So now we have completed the traverse. We have checked the A, and now we will just mark as a this is visited. Okay. If any node which is marked as visited, we never revisited that in the digital algorithm. So that is actually a greedy approach. We are just looking the optimal solution from this source, this node, and after that, after updating the adjacent vertex distance, we will never look again. It's okay. So we are repeating this optimal like greedy approach at the each node. So now after again we will look for which are the nodes which are not visited but has the smallest distance. So this 4 and 7. So 4 is the smallest. So we will look from the B now. Okay. And we will mark as a true. And from B, we will just check. So we have the B to C1. So current distance is 4. 4 plus 1 5. So we are getting again this 5. Okay. So now 4 plus 1 5. This is now updated. And now, what are the remaining vertex? So C only. So we will check from the C also, but there is no adjacent which is unvisited. Okay, so that is uh, like it will not affect anything. So we will mark as a true. So we are getting the shortest distance on each node. So 0 and this is 4 and this is 5. So this is the concept of digital algorithms. but it may fails on the negative weights. Okay, so negative constraints. So that condition is generally like this. So let A, B, and C. Okay. Suppose this is uh, 3, suppose 4, and this is -2, and this is 3. Okay. Now, C, C. Okay, so here suppose we are starting from 0, infinite, infinite. Okay, so now we are checking from A. So A to B will be updated by 4, and this will update by 3. Now we will pick the C node first. Okay, now C node we will mark as a true, and there's no outgoing edge. Okay, now we will check from the B. And from B, there is no node remaining which is unvisited. Okay, so because of that, we cannot update the weight which node we have already traversed visited. Okay, so from B we are getting 4 minus 2 2, but still we cannot visit it. So you can see by this dash algorithm we are not able to get the correct answer. Okay, because our algorithm will return 3, but we can achieve this in 2 by this path A, B, and C. So because of that, this algorithm actually failed in negative bits, okay, as well as the negative bit cycle. So this is the approach for rest algorithm. Similarly, we can use this if we have suppose if we have negative weights, so that can be handled by the Bellman-Ford algorithms. That is another algorithm, and that actually use the dynamic programming approach, and that repeat the process. So like every time we will repeat. So for first node we will repeat the process, and that process will repeat n minus 1 times. So like what is the process for Bellman-Ford algorithms? For every term, so how many times we will repeat this process? So we have 3 nodes, we will perform 2 times. Okay, so we will repeat 2 times. So for first time we will check for every node A, B, C. Okay, for second time we will check again from A, B, C. Okay, so how we are doing? So we are not looking the distance or anything here this time. So we are just picking the node, and we are updating the adjacent node distance. Okay, so we are starting from A, and then we are updating our distance of adjacent. Then we will pick the B. Okay, we are not looking that which node has the smallest distance. We are just following A, then pick B and update the adjacent distance, then pick C and then update the adjacent distance. And then repeat the same things again, A, B, and C, and update the distance. And we will get the shortest path, because the maximum path length is possible in this graph is 2. Okay, so because of that, we are actually uh, performing this 2 times. And we can also detect the cycle here in this negative weight cycle. So how we can detect the negative weight cycle using this Bellman-Ford algorithm? If suppose we apply one more time, third time this process, okay, A, B, C, okay, for this graph, and still our distance is updating. Okay, if still our distance is updating, changing, that means that is the negative weight cycle. Okay, so this is the identification in the Bellman-Ford algorithms. And suppose if any scenario you have where the distance are negative, so you can think about the Bellman-Ford algorithms, okay, instead of dashed algorithm. If your problem contain all positive weights, so you can directly apply the dashed algorithms for shortest path. And otherwise, if graph may contain the negative cost also, you can think about the Bellman-Ford algorithms. Another algorithm is Flood-Warshall algorithm. So that also handle the negative weights, but that is the all pair shortest path. Suppose if you have this ABC3 graph. So currently we are taking one source and getting the distance, shortest distance for other nodes. But for all pair shortest path, you will figure out the A to B, A to C, and B to C, each pair shortest distance. Okay. So any pair of the graph you can take, and you will get the shortest distance. You will get a like a matrix type in the output, where rows are also representing the node like A, B, C, and A, B, C like column. Okay. So in each cell value or cross cell value will be represent the distance from that combination. Okay. So that you can think for the uh, all pair shortest path. So this is the shortest path concept. So the as name is the reflecting the shortest path things. Okay. So here you can think about any shortest path algorithms. So scenario will also be the similar type of things. And yeah, next is week 7. So that is MST, minimum spanning tree. So this is the another concept in the graph algorithm. So what is the MST? Suppose this A one graph you have C D. Okay, and you have the connection like this. Okay, and each weights are given like 5, 4, 3, 6. Okay. So for this tree, what is the spanning tree first thing? Okay, minimum spanning tree is the difference. So spanning tree is the for same graph, we will contain the each vertex, and that should remain the connected. But there is no cycle should remain that graph. So that means we are converting this graph into a tree, and where the each node is connected. Okay, and that is the spanning tree. So here we can make like this one of the possible spanning tree B, C, and D. Okay, 5, 4, 3. So this is the one possible spanning tree. You can see all vertex are connected. Okay. Now, and there's no cycle. We can also make like this A, C, D, and B. Okay, this is another spanning tree possible. So this is 4, this is 6, this is 3. So this is the spanning tree. Okay, we are just figuring out the tree where the each vertex are exist as which are available in the original graph, and each vertex are also connected, but no cycle, without any cycle. But minimum spanning tree is the, so you will get many possible way to get this spanning tree, but among all the possible spanning tree, which contain the total cost that is minimum among all. Okay, so here for this first graph, you are getting 4 plus 5 plus 3. And for this 4 plus 6 plus 3. So 2, you can see the total cost you are getting. 4 plus 5 is 9, 12, and here 13. Okay, so there are another possible ways also possible. So you can take either 5, 4, and 3. So here you will get 12. Okay, maybe you will get more maximum more than this also, so like 5 and 6 and 4, so you will get like 11 and 15 by this way. So which one is the smallest? That will called as a minimum cost spanning tree. Okay, MCST or MST. So this concept, this is the requirement for this problem. So what are the type of problems maybe form on this concept? Suppose if you are if your plan is to like want to spread the fiber optics cable in your city. Okay, with the minimum length of the cable, you want to connect all the stations of the by the fiber network. Okay, and the total length should be minimum of the cable. So that is the one scenario. Similarly, you are connecting to the network of the computers and with the minimum length of the LAN cable. So like this type of things maybe uh, frame using these algorithms. Okay, so to solve these problems, we have two algorithms, Prim's algorithm and Kruskal algorithm. So both are the same, like task is same. Both will return the same output, minimum cost, but approach is different. So you can think about any algorithm. So concept of the Prim's algorithm is similar to very rest algorithm, but it will be changed. So suppose if you have A, B, C, and D. Okay. Like suppose this is the spelling tree, so like 5, 4, 3, 2, like this. Okay, so here you can start from any vertex. Okay, no, there's no need to start from any fixed vertex. You will get the same answer. Suppose if you are starting from A, so you will see what are the vertex which you have. So same things, we will start from 0, infinite, 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 and we are picking the like A. Okay, okay, we will update this. So A, we are looking what are the adjacent of this. Okay, A, from the A, we will pick that. Okay, so now we are looking A to C, A to B. But this time we will not add the previous value on this vertex. Okay, so we will only just look the current edge value. So we are getting A to C is 5, so 5 is will be update here. And we are getting A to B is only 4, so 4 will update here. Okay. So now we are getting, so we have traversed this vertex, and now we are picking, updating the value. And this time we will pick the next smallest value. So 5, 4 we have infinite. Okay, so next smallest vertex is 4, this B. So means this edge is marked as a spanning tree edge because we are picking this vertex B. And from this B, what are the next updates? So from B to D, this is 3. So we will only took this 3, nor we will not add in the 4. Okay, as the style we add actually. So we will only pick this 3 and we will update by 3 like this. Okay. So this is marked as a true. This is also marked as a true. And now we are getting 5 and 3. So you can see 3 is the smallest. So where from we are getting this 3? So from B. So this edge will be marked as a spanning tree edge. Okay. Now we will pick this 3. Okay. So they mark 2. And from 3 we are getting 2. So this will update by 2. Okay. So now after picking this 3, so this is updated. So okay. Now we will just check which vertex is the smallest. So only 2 is remaining. So we will check where from we are getting this 2. We are getting from this D. So that means this will be updated. So you can see we are getting 4 plus 3 plus 2. So this is actually 9. So this is the smallest, and this is the minimum spanning tree. So this is the approach of the MST, sorry, Prim's algorithm. And for classical algorithm, so we follow the different approach. So like A, B, C, D, and this 4, 3, 2, and 5. Here we may actually collect the edge. Okay, so and what are the edge we have? So after that, first step is the collection of the edge. So we have A to C is equal to 5. We have A to B, sorry, A to C, A to B equal to 4. A, sorry, B to D 3, and C to D 2. Okay. After that, we arrange this edge based on their weights in increasing order. Okay. So which one is the smallest, that we will pick. So here, this you can see, this is the smallest one. So we will take the graph again. So A, B, C, and D. Okay. So we will pick this CD first, okay, because that contains the smallest. Okay, so CD we will mark as true in the graph. Then BD. Okay, so BD is now third. Now we will pick AD. So AD is also, we are just considering if that edge is not creating any cycle. Okay, if that edge is creating cycle, we will ignore that. So AC is now, you can see if you connect AC, you will get a cycle. So just ignore this. So you are getting this. Okay, total same for 3 and 9 total. So you can see we are getting the same output. Okay, so here might be the 3 may be different, but you will always get a same total cost. The 3 may be different if the you have the duplicate weights in the graph. Okay, so this is the spanning tree concept and minimum spanning tree, so that you can see to solve. And now BK is the next thing, that is the maximum flow network. Okay, so this is the different concept of the graph. And so here we have some constraint like A, suppose if you have A is, sorry, not A, I'm taking that starting vertex. Okay, so like S and T. Okay, so this is called as a source and this is called as a sink. Okay, and in between you have the network. So like A, B, C, D, like you have the network with some capacity. Okay, like this. Okay, so each edge also has some weight values, like this is 4, this is 5, and here this is 3, and here this is like 2, this is 1, or this is like 1, this is 3, and it's 4, like this. Okay, so what is this representing actually? So flow means we have some source that is actually giving the some flow. Okay, so that you can see that is generating the flow. So 4 and 5, that is generating total 9 flow. But in between some that nodes are there, so that are just like a place. And so yeah, so what are this actually written middle value is representing? So that is representing the capacity. So all each edge this value V5, this is representing the maximum capacity this edge can handle. Okay, at a time. So similarly, this is the three maximum capacity A to B can be handled. Okay, so A B to this is can be handled, and this is generating unlimited flow, but we have the limited capacity on each edge in the network, and here we are receiving the flow. So if this constraint is given, some constraints are also there with this type of problem. So that constraint has some how much flow we are getting on the any node. Output maybe output actually can be only the similar same. Input flow should be equal to the output flow. Okay, like this, and we can also not flow more than the capacity. So some constraints are there. This step I'll show you the constraints also properly. But the problem is what maximum flow we can achieve from this S to T. Okay, so that is actually a max flow problem. Max flow. Okay, so constraint I have in one another document. So let me show you that. Hmm, So you can see. So first see, a flow network is a directed graph where each edge has a capacity. Okay, so this is the first term. Each has the maximum amount it can carry. There is a source node where from flow start actually. The sink node where the flow ends. Flow must obey rules called flow constraint. So this is the constraint rule. So think of it like a water pipeline system. So you have the pipelines in pipe are as water as flow, pipe thickness is capacity. So you can relate this network as a pipeline network. Okay. What are the flow constraint have? So capacity constraint we have. So an any edge, flow on any edge will always be less than equal to its capacity. Okay, like this. So example, if a pipe can carry max 100 this is the like capacity, you can't send more than this. Okay, at a time. So here's some constraint is given per minute. So per minute here this you cannot send. So this is the capacity constraint. Skew symmetry, flow can be reversed in the residual graph. So this is the different concept. I'll show you the example. So here we can identify that the any another possible flow is there or not. So flow conservation. So this is another constraint. So except for source and sink, the total incoming flow is equal to total outgoing flow at each node in between. Okay, there is no water lost at intermediate junction. So this is the problem, and our goal is to identify the maximum flow in the network. Okay, so we have the algorithms, the Ford-Fulkerson algorithm or Edmond-Scarp algorithm. So that we have. So let's I make this graph. So let's see and solve this how we approach the problem. So here we use the BFS technique also to improve the efficiency. Uh, okay, so like S we have and we have the T and we have S to A suppose. Okay, and we have this 10 and S to C we have uh, 10 and A to B we have 4 and A to C we have 2 and C to B we have 8 capacity, B to T have 10 and C to T we have this. Okay, 10. So suppose this is the network. Now how we can identify the flow on this net? So here uh, hmm. Okay, before going to this graph, let me just take one simple example so that to explain the problems on this. Okay. Oh, sorry, I removed that. Oh, we can reverse back. Okay. So S T. Okay, and now we have this A and then B. Suppose you have this 2 and 2 and this is 1, this is 2. Okay. Let me check that for 1 second. This correct example or not? Oh, sorry. Okay, let me just show you the correct example. Some value is different actually. Where it's that? When below. Okay. Inside. Okay. So let me show you that problem. Yeah, so this is the problem actually. One. Okay, I missed that. So suppose if you have this S and this T and A and then B. Okay. So what is the problem actually in the normal approach? Suppose each edge has one capacity in this network. Okay. And according to the first algorithm which we have seen, so that approach algorithm actually use the approach. What we can do, we can figure out the possible path. Okay. And we will just pick the maximum capacity we can flow on that path. And after that, we will reduce the capacity on that. Okay. So first, in this graph, we can pick randomly S, A, and T. Okay. S to A and then A to T, this path. So what maximum flow we can use achieve in this path. Okay, so that is just pick the minimum capacity in this. Okay, so one you can pick maximum one. After picking this capacity will become zero, and this will also become zero. Okay, so by achieving this, after that, what other possible path we can achieve? So zero path we cannot use because capacity is now no capacity is remaining. Now we can pick S, B to T. Okay, and with the same maximum one. And when we are picking this zero and this is zero. So now there is no possible path from S to T with any capacity. Okay, so because all become a zero. So now what is the total flow we have achieved? Total two. So this is the way to calculate. But there is a mistake in this. There is a error in this. Suppose we are picking the random path. Okay, so suppose if we pick first attempt like A. Okay, like we first remove this. Not like this. Delete from here. Okay, now I'll pick the different approach. Okay. So suppose if I'm picking the first path as a S to A, then A to B, and then to T. Okay. So now I am picking this like this. Okay. So we are getting the one, but after that it becomes zero, it becomes zero, and it becomes zero. Okay. Now you can see I cannot pick any because if you are picking S to B, now you can not move to B to T. Okay, because this is zero capacity. So you are getting only maximum possibilities one by this approach. Okay. So algorithms actually follow the rule to create a residual graph after selecting any path. Okay. So after selecting any path, you will create a residual graph. So what is the residual graph actually? So after getting this path, what actually flow we have selected, we will create a reverse path for that. Okay. So that is reverse path. I need another pen. So we will create a reverse path, okay, on the same path which we have used, and we will use the same capacity what we have used. So that is one, that is one, and that is one. So now adding this reverse path, okay, first we have selected S to A to B to T. We will create a reverse path with the same capacity which we have used in this path, okay, which we have, okay. Now after getting this, we are getting the residual graph. This is called as a residual graph. And again we will see with the by including this residual edge, we will see is there any another possible path is available now or not. So you can see if we will see S to B, we can move. Now B to A, we can move with the help of this residual edge. So this now we are getting S to B and to A and to T. Now is in this you can see 0 and 0 and 0 we are getting. So we are getting one more. So in this way, now still if you create again residual graph, so one and then now one and now one. Okay. Now you will not get any path from S to T. Okay, so now you are getting correct answer too. So this is the first algorithm that follow the things. Another next algorithm is the different version of this. So that actually picks always the shortest path from S to T. And I have already mentioned shortest to calculate the shortest path in the terms of minimum number of edge in the path. So we use the BFS algorithm to figure out this. We figure out the what is the shortest path from S to T. We will pick that order first. Okay, so S to A to T we can achieve and S to B to T we can achieve. So first we will figure out one path S to B to T. After that we will remove this path and then we will check the next shortest path using the BFS. So in this way you will get a correct answer. So that is the another algorithm that improve the efficiency. So this is the algorithms of for maximum flow. So you either you can create the residual graph or things, or you can use the BFS approach. So that's our two algorithm basically we use. So this is the first algorithm you can see Ford Fulkerson algorithm that calculate with the help of residual graph, and this Edmond Scarp algorithm actually use the BFS to always pick the shortest augmented path. Okay, and here we actually achieve the complexity also. So this is the network flow actually algorithm. And so like next week 9 actually will be on the same topic, but that will be depends on the min cut actually. So what is the min cut concept? So in the same graph, okay, so what are the edge? If we remove that edge, this graph will actually become a disconnect from S to T, and that is where it should be equal to the maximum flow. Okay, that is called as a min cut. So like suppose if we remove this as AT and BT, okay, so if we add both capacity 1 and 1, we are getting 2, and that is the maximum flow value. And after removing this edge, you are disconnected from S to T. So this AT and BT are the set of edge that is called as a min. So min cut means remove the edge with the minimum uh, edge cost. 1 second. Minimum edge cost, total minimum edge cost, and where the our source vertex should be disconnect. The source vertex will disconnect to the sync vertex. Okay, and that value will also always be equal to the max flow value. So that is the min cut things. Okay, so that will be come in the week 9 concepts. After that, week 10 is there. So week 10 is DP concept. So DP, regarding the DP, we will conduct one another session. So we'll give the idea of DP. Okay. So regarding the more problems, so we have also created one. You can see this portal link in the same portal. This notes GitHub notes. I'm sending in the chat. Okay, so in this link, you can see last tab, competitive problem for practice. Okay, so here we have created a one more page. So here you can directly move to this another page. Vikrant Mehta, this is our one student that have created this. So you will jump to this another page. Okay, here you can see we have filtered some problems based on these concepts. So like you can see graph algorithms, DFS based problem. If you will click on any like sorting, stack queue, graph, union, find, balance, divide, and conquer, dynamic programming, here you will see some set of problems from the lead code actually. Okay, so those who are very beginner in the competitive programming, then those who can take the help of these. Here we have taken some set of problems which are based on this concept. Okay, so sorting and searching, stack based, we have filtered the problem from lead code. Okay, and we have explained the like approach to solve this problem. Okay, here you can see we can explain the uh, understanding of the problem as well as the solution approach. Okay, and after that we have given the implementation solution also. To for practice for this problem, you can directly click on this link and you will directly jump to the lead code. So what you can do, you can just go through this explanation. You can first understand the problem and go through this explanation and just move to the lead code platform and where you can solve this problem. Okay, if you are getting difficulty to solve problem, so that is taking time to load. Okay, let me again what separately. So if you are getting like any difficulty to solve the problem, you can also see the solution by this. Okay, need help for implementation. So before that, after getting some idea or approach, just try by your own and then check on the lead code. So this will open. Maybe it is taking some time to load, but that will move to the lead code platforms. Okay, so to solve this problem. So here we have collected the problems, some 7, 8 problems for each topics, and that will also help you to figure out the approach to solve the problems. Okay, based on some difficulty, not difficulty topic wise. Okay, and you will get some idea then how problems may be framed on the different concepts. You will get. Okay, so all these problems are from the lead code. Okay, so now this is all about for today. If you have any query, you can ask. Or we have already previously also mentioned, you can also take the help of Discourse forum, Google forum. You can post your query on that forum. If you have any course related query, you can post. We have received many like questions on, I'm not sure how you are getting the course. Okay, any query, anyone? So let me share this link also separately. Okay, so you can reach to this link from the same above link, but I have posted the separately also. Yeah, you can see this. So this is open. Yeah, this problem is open. Now you can write the code in this here once it will load. Okay, so you can practice by this. So approx 50, 60 problems are there. So you can practice on this also. And these are very basic and it's a beginner level problems. So you can build up your confidence level by solving these problems. Okay, so this is all about for today. If you have any query, you can ask. So how can we improve our timing to solve these questions? Yeah, so timing efficiency. I hope you are talking about the timing efficiency. So definitely you should know these algorithms first because these algorithms actually provide the efficiency. Okay. If you are after getting the problems, if you are directly thinking for the naive approach, okay, then suppose if you are getting the sorting problems and the sorting problems, there are many sorting algorithms, and you are trying to some naive approach for that. Then think about some different solution approach. I hope to get this time efficiency idea. You should know some time complexity understanding. Okay, that is also given in our notes. So like first week 2, you can see. But if you understand these algorithms, all these standard algorithms are actually efficient algorithms. So if you know use these algorithms, definitely you will get the efficient solution. So like searching example, searching if you are using linear basic concept, just comparing each element by you, so you will get a order of n time. But if you apply the log n binary search, okay, then you will get a log n time. So for that, you have good understanding of these algorithms. So that are actually efficient algorithms we have in this. And because of that, today I have discussed these algorithms because these are the core behind the competitive programming for the efficiency. Okay, so go through this, and when you are writing any solution, so compare that solution with the another possible solution. Now the AI is there, you can also get multiple type of solution and compare. So how much, what is the complexity for your code? Okay, so I'm stopping sharing. If you have any more query, you can ask or you can write in the chat. Okay, so we have released the solution till week 5. So we will release the remaining 2 week 6 and 7 once the week 7 will complete. So we are releasing 2 to week 5, and you will get the idea of uh, okay, how we are approaching the solution. Okay, if there is no query, then we can bind up the session. Uh, thank you everyone. Yeah, host, you can close the live stream.